Hello all, hope you guys are doing great. Today I will talk about a peculiar topic which often baffles the classical laws of physics. Yes, you guessed that right. It's related to quantum. In fact, a simple application of it. Quantum cryptography. We'll discuss about what is quantum computing, what is cryptography, what is quantum cryptography, even develop a simple application in it to understand our learning. So without any further ado, let's get started. What is quantum computing? Classical physics failed to describe the behavior of small things, which was overcome by quantum physics. Quantum theory explains this behavior and gives us a more complete insight into our universe. Scientists have realized that this previously unexplained behavior of performing certain computation, which previously was not possible, is quantum computing. It basically distills the core concepts of the quantum physics into its simplest forms. Here I'm using the Qubit package and the NumPy library. I initialize it. Now representing the qubit states. Classical bits are well defined, having either state 0 or 1. In quantum model, vectors are representing the qubit states. Just like here, we use the Dirac notation. This is ket 0 and ket 1. These are column vectors. We initialize the quantum circuit using the QC object and with the initial ket1 in the draw text method. Now, what are single qubit gates? Of course, for computation, you need gates. Even classical computation has AND or NOT. In quantum, we have XYZ gates, Hadamard gates, and XYZ bases, which are new. Hadamard gates are basically used for transforming from one base to the other. Initial bases are in Z and initial qubit is 0. Here we change from the common Z base to the X base using the Hadamard gates. We basically transform it into the X base. Now you may ask, why quantum? The reason is the big O notation. Now what is big O notation? It is basically the time complexity involved for any algorithm. If we take the factor of n fact lower the number of bits involved, the number of operations is on a greater scale. With the example of the RSA algorithm, RSA 250 is 829-bit number, which on factoring can take almost 2700 co-years, which is of course very great. What is cryptography? Cryptography is the science of data encryption with number theory at its core. Symmetric key cryptography is one which is shared between the sender and the receiver. These modern algorithms have come, which are MDA, MD5, and SHA-1, which are even used in blockchain. Now, what is quantum cryptography? Applying the concepts of quantum mechanics and with cryptography, we come at an algorithm which provides such insight. BB84 protocol is used for the communication in quantum channel. Let's take an example to understand it better. Here, Adam is the sender, having message in bit form, and according to which he has bases set up in quantum. It passes through the encoding function, which results in the ket1, ket0, depending on the base involved. Now, the difference between a quantum channel and the physical channel, quantum channel is basically used through the fiber optic cable. Photons are transmitted through it, in which polarization occurs and states are decided. In classical channel, the receiver or the sender has to trust the channel mediator, which is Eva in this case. After encoding, the receiver, Brian, measures the message bits, and generates the qubit states at random. He keeps the measurement results private. Now the sender and the receiver both share the bases commonly. If the measured state is the same, part of the shared key is taken as good bits list, else it is discarded. Now, using the sample bits function, we get a sample of key generated. If it matches, the transmission is successful. Now, if the interceptor comes in, what happens? The interceptor measures the bits here in the quantum channel, which changes the basis of bits being transmitted. And Brian receives another set of bits, which lets us know what is going on. Well, going back to our example, here is the BB84 protocol described. We defined a single qubit and a classical qubit with the edge gate and the barrier. This is without interception involved. Here, we can see the circuit diagram and the probability of getting correct is maximum. With interception, now Adam sends the qubit to Brian, but Eva interrupts it and measures the qubits, which basically changes the states involved, and we get the probability being misinterpreted. Now, a real application, which I described priorly, is encode the message. Three functions are involved: encode the message, measure the message, and remove the garbage with the sample bits. In case of interception, e-bases are generated and we measure the message here, due to which the bases change and the complications arise. And if the states do change, we get the alarm rate false. Now, what does the risk analysis or risk aversion? We conclude that lower the qubits, lower is the chance of getting caught by intercepting, and higher is the qubits, higher is the chance. Now, if we lower the sample size from 15 to 4, we can see that Eva went undetected. Now, the question arises, how can we use it to secure our systems? The field of quantum computing is evolving at a much larger pace. To catch up with it, we need to understand its fundamentals. Of course, there's much more to this video, which we will cover sooner or later. Currently, quantum computers are able to process 1000 qubits at once, which is roughly 125 bytes. It is not even able to transmit even a single text file. So using it for your menial tasks is out of question. Of course, sooner we will be able to tackle various problems. Let's hope for the future. That's it for today. Hope you find it interesting. If you do, please share it with your friends. Thank you. Signing off.